And electron volts are going to be important for the rest of the course. And the reason is, what's the standard unit for energy? Joules. But for the rest of the course, we're going to be focusing, remember, on things that are at the atomic and subatomic level, very small, and the joule is too big a unit of energy to be convenient there. So even though we'll still be working with joules, we'll also have to work with electron volts. This is a much smaller unit of energy that's more appropriate here. Okay, so volts are a unit of potential, but electron volts are a unit of energy. We'll probably have to talk about that a little bit more in a couple seconds, but let's keep going for now. So the work function here might be 5 electron volts, which means that it would take 5 electron volts to pry an electron free. Well, let's say that somehow we were able then to deliver 3 electron volts. It seems like that wouldn't do it. That would not pry any electrons free. If we delivered 5 electron volts, it seems like that would be enough to pry the electron free, but just barely. And how about if we delivered 7 electron volts? Well, not only would that pry the electron free, but then we have 2 electron volts left over. So what are we going to do with that? Well, theoretically, one thing we could do with that is try to use that to pry another electron free, or maybe that could just go to the electron that got kicked off. The electron maybe would get that extra 2 electron volts, and then not only would it be pried free, but it then would be moving with a kinetic energy of 2 electron volts. By the way, all of this that we're going over now, this is just what people would have predicted when they thought that light was a wave. And then in a second, we'll see some of these predictions came true and some did not come true. So we need to see what the prediction would be, and now then we'll see how this is in some ways similar, in some ways different. But the basic idea is, if more energy comes in than is necessary to satisfy the work function, it seems like that extra energy could go into 2 places. Theoretically, it seems like it could go into prying more electrons free, or it could just go into giving this electron more kinetic energy. So the 2 things that we want to measure here is how many electrons are pried free and how much energy do they have when they're leaving. So if we increase the intensity, we've already seen that seems like it's delivering more energy, so we should get more electrons free. And also, what should happen to the kinetic energy of the electrons that are freed? Should on average be bigger or smaller? Because again, we've got tons of energy. It seems like that extra surplus energy might go into not just prying free more electrons, but giving them more kinetic energy. If you only put in barely enough energy to pry free an electron, it would have 0 kinetic energy. It would kind of be freed and kind of just sit there in the theoretical limit case. But if you put in more than enough energy, maybe that goes into its kinetic energy. All right. Also, we know that waves have frequencies and wavelengths. So when they were making their predictions, you remember if you change the frequency of a wave, how is that psychologically perceived?
The cycles over second.
It has more cycles per second, but of course you don't psychologically perceive it that way. If somebody is creating light with a higher frequency, how can you tell by looking at the light that it's got a different frequency? What's the difference?
By looking at the light is the different colors.
The different colors, that's right. High frequency would be like violet end of the spectrum. High frequency would be like the violet end. By the way, if someone increases the intensity of the light, how do you psychologically perceive that?
Intensity of the light would be the brightness.
That's right. So this is brightness and this is color. By the way, wavelength is also color because frequency and wavelength move inversely to each other. This is the brightness. Well, it makes sense that if you make the light brighter, it's going to kick off more electrons and there'll be more kinetic energy per electron because the brightness means there's more energy. Now, how about if you change the frequency? Well, the prediction was when scientists thought that this was just an ordinary wave and they looked at the frequency, they said, well, changing the frequency should have no effect. This was the classical prediction, that changing the frequency should have no effect. Because it doesn't seem like the frequency is directly related to the energy. It's the intensity that tells you the energy. It doesn't seem like the frequency has much to do with the energy of the wave. You could have different frequencies and still have the same intensity. So the point was, suppose you increase the frequency while keeping the intensity constant. Well, if you're keeping the intensity constant, you have the same number of joules per second per square meter, so it seems like this would have no effect. These, again, are the classical predictions. And we'll see in a second they were in some ways right, but somewhat wrong as well. Let's see what actually happened when we shone the light on the sample here. So let's say you start with light that's got a very low intensity and a very low frequency. Well, basically we get no electrons freed. No electrons are freed from the sample. Of course, in this experiment, they had a detector over here to detect the electrons that were coming out, but we won't go into those details. Well, this is what we would have predicted. Low intensity means low energy. But now let's say we have high intensity and low frequency. So by the way, how would this be psychologically perceived? This would be dim red light. Low intensity means that it's dim, and low frequency and high wavelength means red light. So this is very dim red light, or even infrared if we were using non-visible light. Now let's say we have high intensity and low frequency. How would that be psychologically perceived?
It would be seen as bright and red.
Yeah, very bright red light. All right, now the prediction was that now we should get tons of electrons coming out, because now we're putting in a lot of energy. We're putting in tons of energy over here, but they still got no electrons. No matter how high the intensity was, they were not able to get any electrons with this low frequency light. And this was very mysterious because they could be putting in, I don't know, millions of joules per second per square meter. It seems like there's plenty of energy to free the electrons, but it wasn't working. So this is not matching our prediction. On the other hand, suppose we have low intensity and high frequency. Well, how would this be psychologically perceived?
As dim violet light.
Yeah, and now we did get electrons. It was only a small number, but now they were getting the electrons freed, even though the intensity was very low, so it didn't seem like they were delivering a lot of energy. And what happened as they started increasing the frequency here? They increased the frequency even more. So what happened when they increased the frequency? They got higher kinetic energy per electron. Higher average kinetic energy. Some electrons shot off with high energy, some shot off with low energy, but on average they were having higher kinetic energy than before. Again, this didn't match the predictions at all because it didn't seem like frequency should have anything to do with the energy. It seems that that should just come from the intensity. That's the energy per second per square meter. And finally, what about if they had F constant and I increasing? Well, then they got more electrons freed and the same kinetic energy per electron. Now remember that if the frequency was very low, there was no electrons at all, if there was freed at all. Frequency was very low. Low, what's that? Yeah, frequency low. When the frequency was very low, no electrons were freed at all, which again seemed weird because it seems like that should depend on the intensity, not the frequency. But if the frequency was high enough to get some electrons freed, once the frequency was high enough to get electrons freed, if you kept the frequency constant, increasing the intensity gave you more electrons freed. But it didn't change the kinetic energy per electron. And again, that seems weird. It seems like since you're delivering more energy, some of them should have more energy than before. All right, so there's lots of things that you couldn't explain just in the old wave model of the light.